Good morning or good afternoon. Welcome to May 2025 IBT/ABC UTC monthly webinar. We are delighted to bring to you this month a topic on FRP top girder bridge. And with us, we have Habib Dagger and Ken Sweeney and Tim Kenson and Anthony Liba with us.
I'm Habib Dagger, Director of the Advanced Structures and Composites Center at the University of Maine. And the technology of the top girder technology was developed at the University of Maine. And so I'm going to give an overview of the center where the technology was developed and some of the engineering work that was done in developing the technology. And then following that, Ken Sweeney is going to talk about the spin-off company, Basalt International, that actually spun off the University of Maine to produce these girders. So the Advanced Structures and Composites Center has been in the business of doing composites for 27 years right now. We have about 400 employees at the center. And you can see some of the different composite applications on the screen that we've worked on. One of them is the bridge in the backpack, the composite tub girders. We've used composite stay cables on bridges and composite boats and so on and so forth. This is a view of the Advanced Structures and Composites Center at the University of Maine. We're the largest university-based research center in the state of Maine, established through the National Science Foundation in 1996. We're about 100,000 square foot lab at the University of Maine, and our strength is in material development, structural engineering, and manufacturing applications of composites. The center has received a large number of awards over the years, so I'm proud of the team that's done that, including the 2015 Transportation Champion of Change for the work we've done on composite bridges for the White House, as well as Engineering News Records, Top 25 Newsmakers, American Society of Civil Engineers, Charles Spanko Award for Innovation for the work we've done on bridges, and the American Council of Engineering Companies Engineering Excellence Award for the US. One of the bridges, the first bridge that was built using the tub girder technology is in Hamden, Maine. It's called the Grist Mill Bridge. You'll be hearing more about that in just a short while. This is where Maine is, on the northeast corner of the United States, and the Grist Mill Bridge is where the red item is, and you can see what it looks like in the right-hand screen. This is a short video of the construction of the bridge. You can see what the tub girders look like. They're very hollow tub girders with pre-installed connectors that connected to a concrete deck. The girders were light enough that the contractor chose to pick them up two at a time. That's one advantage of the technology. And you can see the utilities are pre-attached. That allowed us to install the girders in half a day. And after the girders, of course, are installed, then you put a concrete deck on, and it could be a precast concrete deck or cast-in-place concrete deck. It could be longitudinal or transverse. But you can see here the advantage of this technology is how light those composite girders are. The other major advantage is the connectors used are removable. So when you have to replace the deck in 30 or 40 years, you don't have to jackhammer it. So those connectors allow the deck to be released. So it could be cut and rather than jackhammered. So it makes the removal of the girders a lot easier in the future, or the deck a lot easier in the future. This is what the cross section of the deck looks like. So this is the tub girder. It is a composite section that's solid in the flanges, top and bottom flanges, but it's cored in the web. There's a foam core in the web. The bottom flange uses carbon fiber to increase the stiffness, but the majority of the stiffness on the system really comes from the concrete deck, and that's the composite technology here allows us to meet stiffness requirements for this technology. As you can see, the girders are spaced typically could be 5 or 6 or more feet apart, depending on the bridge. The depth of the girder could vary, like any other girder. The key here is also the shear connectors, as I said earlier, that are removable. So in 30 years or 40 years, you can unbolt them from the bottom and pick up the deck in pieces rather than have to jackhammer it. The other thing you'll see on this technology is the girders, the webs are inclined, which allows us to actually stack the girders together and nest them on the truck and ship them out. They're light enough that you could do that. Here's some examples of why we developed the technology. One is the ability to have lightweight girders and ship a lot of them on a truck. And here's an example of 53 girders that could be stacked or nested that way. Of course, you have to meet clearance requirements on that. They require minimal maintenance because they're made out of composites. It allows easy replacement for the deck in the future because we believe the girders will outlast the deck. And then you need very small cranes because they're lightweight and you can pick them up and put them down. Whereas if you had steel girders, you're limited to the number of girders you can put on a truck, and you need heavy cranes to actually install the girders. So that's some of the advantages of the technology going forward. In terms of design, we use LRFD technology in designing the bridge decks, very similar to what you would do with a steel plate girder design. And we'll be talking more about design technology later. There's been years of development on the technology at the university. We've done many static and fatigue tests on this girder technology, different girder sizes, different girder spans. This is an example of a test that was taking place, examples of some of the results of the testing to compare predictions to actual test results in the lab. Here's an example of one girder, a load deflection tests that showed that the girder did carry 2.65 times the strength 1 factored load, which is what we were shooting for in this particular case. In terms of fatigue loading, we've done again a number of fatigue loads. Typically, the fatigue loads will take about 3 months, and we'll run to about 3 million cycles of fatigue loads. You can see here mid-span deflection versus fatigue cycles for this girder technology. And then we've developed fatigue life prediction models for these girders as well that you'll hear more about. All of that's being put into an AASHTO guide for this technology. Another big part of the technology I talked about earlier is the unique connectors. These connectors that we use provide the static and fatigue resistance needed, simple to install. They use this stainless steel threaded rod system and a corrugated face on the top flange of the girder. And that corrugation on the top flange of the girder allows for shear interlock between the concrete and the deck. So the shear forces between the concrete and the deck and the girder are really carried by these corrugations, and the vertical threaded rods are simply there to prevent uplift, if you wish, of the girders. And so these connections have undergone years of static as well as fatigue tests, as you see here on the right-hand side, to make sure it meets the criteria. So it's a shear friction connection. A lot of the R&D that's taken place as well is about how to predict the shear strength of these webs. These are complex cord sections, so predicting the shear strength and the buckling strength of these webs is a big part of what we've done over the years. You can see some of the modeling and simulations using FEA modeling, as well as on the right-hand side, some of the picture frame tests we've developed here to look at the predictions of the shear strength of these. And then we've done a lot of field load testing. This is a field load test that we've done on the first bridge we built in Maine. We had 50 strain gauges on the girders. We had 4 trucks that produced moments on 2 lanes that are equivalent to the HL93 plus impact. And we recorded flexural as well as shear strains from different load cases. And that's part of, if you wish, the body of knowledge that was published to provide the technology needed and eventually AASHTO codes required to put this technology into practice. And this is a list of journal papers that describe the technology. There's a large body of information if you're interested about how we predict shear strength or fatigue strength, the load testing was done. All of that has been published in leading journals, if you wish, in the field. So you can always go back to that if you had additional questions. So this is the background that led into us spinning off a company at the university, from the University of Maine, called Basalt International, that is producing these girders and building them. So,
Sweeney speaking. This is just a slide that shows it's kind of like a company overview, and really an overview because we flew it with a drone. You can see our facility on the left-hand side, and one of the bridges we're going to talk about today, the Stillwater Bridge in Orono, Those are the girders that we're fabricating presently for that bridge, and we'll get into a little detail of that later on the technical part. And over on the right is the field load testing of Grist Mill Bridge, which Habib passed off to me. So these are some of the completed bridges. There's 4 of them right now with the CT girder bridges. Grist Mill Bridge is in Hamden, Maine. Sun Island Bridge in South Pasadena, Florida. Twin Bridge also in Hamden, Maine, and the Cottrell Bridge in Westerly, Rhode Island. So there's been these 4 of these are in place and serving the communities well. The construction of those bridges went very well. Contractors, once they saw what was done and how it was done and the lightweight, they want to know, are we going to do more? And we hope to. So these are other pictures of these bridges that are in service today, and these are some of the construction photos. And then you can see the Twin Bridge in Hamden. That was a double T type bridge. You can see it on, and also the Cottrell Bridge in Westerly. And the girders were manufactured, and then the precasting was done in a plant, and then they're loaded, they're installed as modules on the bridges. The interesting one, Sun Island, that was one where we shipped the girders on a couple trucks to Florida from our plant in Winterport, and the contractor did the precasting in his own yard, and then transported them to the site. So it was a similar one, but the precasting was done in the contractor's yard. Cottrell Bridge was the other one, and that one was done in a precast plant in New York. So we'll get to the main event here, which is the Llewellyn Estee Stillwater Bridge, and it's actually 2 bridges. It's in Old Town, Maine, and right now the progress of the construction is they've got the temporary detour in, and they've demolished and removed Bridge 1 and Bridge 2, and they're in the process of putting in the substructures as we speak today. Bridge 1 is a 75-foot span, continuous over the pier, 10 girders, and Bridge 2 is 95-foot spans, continuous over the piers, 15 girders. And the other innovation here is that they have integral abutments, and the drilled shafts also have an FRP casing around them. So this is a CMGC project. We were there in the beginning, in the early parts of the design and the selection of composites. And you can see the partners on the CMGC team members that were part of the contract. And we have some big names there: HDR, WSP, obviously University of Maine. Reed & Reed is a contractor on the job, and it's owned by Maine DOT.
All right, now that we've gone through a brief overview of the Stillwater, we'll dive a little bit more into the details and some of the technical innovations that are related to this particular project that we've added to the initial 4 installations that Ken already covered that are in service today. As part of the CMGC project procurement method, we evaluated several different alignment options and span configurations. What landed in the end was an on alignment design with the 2 bridges, and as Ken mentioned, the Bridge 1 is a total of 152.5 feet, comprised of 2 75-foot on center spans continuous over the pier. The bridge width is 42-foot 2 out to out, consists of 2 11-foot travel lanes, 6-foot shoulders, and a sidewalk. And both cross sections are comprised of 5 CT girders that are spaced 8 foot 5 inches on center. And the superstructure depth here is 5'3" for both bridges, using the same cross section for both applications. It does feature some unique attributes. It is a corrosion resistant reinforced concrete cast in place deck, so it will utilize both GFRP rebar and chromium, high strength chromium steel for bent bars. And one of the things we'll cover in a little bit more detail today is some of the details surrounding the integral abutments with this girder technology, as well as the continuous over the pier. I will point out that we did design similar to the presentation that was mentioned before we started about the steel bridge. It is designed here as simply supported for dead loads and continuous over the pier for the live load. And just a quick overview of the plans and elevations for each bridge, showcasing that it is an on alignment. There's no skew here. It is a tangent grade of 0.5%. So pretty straightforward geometry. There's nothing too difficult to work around here from a geometry standpoint. And for the cross section, as we mentioned, it's 5 girders. We do have two travel lanes, 2 shoulders, 1 sidewalk. We are utilizing an aesthetic concrete bridge rail. The girders are spaced 8 foot 5 inches on center. And as you can see in the cross section on the right, these girders are 4 foot 1 inch deep. We have a 8-inch cast in place reinforced concrete deck over the top. And the girder width at the top is a 4 foot 4 out to out. The bottom flange is just under 2 feet wide, showcasing that tapered web, as Habib pointed out in the early part. One of the things that we like to do when we get into complex designs is to optimize the cross section. It's one of the things that is easily done with composite materials. And this showcases what we've done on Bridge 1. So there's 4 zones along the length of the girder. The very end zone that's kind of, that you see the hatched pattern on both ends, this represents a portion of the span where there's a concrete infill to get the continuity, both here on the left at the abutment end. So this will be part of the integral abutment. There's a piece of concrete inside the girder connected through with shear friction. And then this represents the longer one here is for the pier. And along the length of the girder will vary the thickness of the materials where we need it. So bottom flange, which is primarily designed to carry our moment resistance, we will increase the thickness of the bottom flange as we approach the midspan, or we will increase the amount of carbon. So you may actually see there's a decrease in thickness, but it's actually an increase in the amount of carbon and the stiffness of the section. And kind of on the opposite, we'll do the same with the web, where the web will become thicker towards the supports where we need increased shear capacity, and it will taper off toward. We've done this for both bridges, both sets of spans, changing where those zone transitions occur, really so that we optimize the use of materials. We're not providing over capacity where we don't need it, and not utilizing the materials where we don't need them. So we do optimize that. We, as Habib mentioned, we do use the LRFD design methodology for this. We'll touch a little bit later on the development of a guide specification for AASHTO that will incorporate some of the design guidance. But on the load side of the equation, everything is the same. We're still designing to HL93 highway loading, or as modified in our case here for this particular bridge. Maine does modify the HL93. And on the resistance side, we do have a few things that are unique to this material type that we apply, both an environmental reduction factor and a statistical reliability reduction factor. And these are applied to longitudinal tensile stresses and modulus to account for the environmental effects, and for the lack of statistical reliability is to account for the lack of industry adoption. We want to capture that there aren't as many of these in service, and so we want to capture that there's some variability in material properties or workmanship. And of course, the resistance factors are standard, just like you'd have with steel or concrete. And those references there are what we currently use until the guide spec for this girder technology will be published. And then I'm going to turn it over briefly for Anthony to cover some of the distribution factors and how we calculate moment capacity.
Yeah, so as Tim said, we are using the LRFD approach in AASHTO. And so in AASHTO, there is different equations for distribution factors. Now, because of the similarity in rigidity of the girders with concrete girders. We have likened them to using the cross-section C in the actual tables, which is concrete box beams over, or a concrete deck over concrete box beams. And those distribution factors have closed form equations, except for, when you're not in the range of applicability. And with that, we can calculate moment and shear distribution factors. However, a number of times we end up having to use also the lever rule, which is also part of the design methodology. And this is an example here for this bridge where we had to use the lever rule, where the single lane controls over the exterior girder. And so this isn't anything new for a structural designer. You have one lane of load going over on the exterior girder is going to see most of that wheel load from half of the axle, and then almost half of the other axle too, and you end up with a controlling distribution factor there. Now, in the future and even in the past, there has been different FEA analyses that were done and compared to the field load testing, and so that can be an acceptable approach to doing distribution factors. But there were also some closed form equations that were developed that are also going to be in the future AASHTO guide specification. As for doing the moment capacity for this section, I kind of used here a simpler design for the Rhode Island bridge. So these are the numbers that you are seeing in front of you. So there's nothing made up here in terms of how we analyze the section. The moment capacity is determined by strain compatibility, equilibrium, and the constitutive relations that every structural designer would know. So your section, you have your geometric properties. So you have your thicknesses of all the material and widths. You have your modulus of elasticity for all of the materials that you are using for the different laminates. And then failure, the moment capacity failure, is defined by the first material to reach its ultimate strain, which either can be the bottom flange in tension or the concrete in compression. In a lot of designs, it is more favorable to have the bottom flange reach its tensile failure strain. And so that sets the strain at the bottom flange. And with that, you have linear strain profile over the cross section. So now you have the strains in all of your materials, and multiply the strain by the modulus of elasticity, you get the stress. Multiply the stress by the area of the material, you get your force. And once you sum up the forces around the neutral axis to get zero, that's how you can find where the neutral axis location is. At that point, you just find your moment capacity by multiplying the force by the moment arm. So it's a number of times, for someone who's used to using the code, it's not a closed form equation right away, but it's a simple way to get to it. A number of our designs also have the optimized cross section, where we do this analysis for the different sections based on the different laminate properties. An alternative way is simply to do that's basically the transformed section analysis. And with the concrete, we also use the Hoggenstad equation. And that's simply because the concrete, and a lot of times, is not utilized close to its F'(C), and so the Whitney stress block doesn't always apply. So I'm going to move on to talk about the integral abutment details that we are using here. So with having the shear friction connection at the end in the webs also makes that the concrete and the FRP section at that point are in composite action, which means that now the stresses are also transferred from the FRP girder into that concrete block that's at the end. And that is what is tied back into the abutment. So this is some of the details of how the rebar is detailed with all the stirrups, and how the rebar from the deck goes also into that connection detail. And this is where we went back and forth on this project on how we want to do the simple spans. The first idea was maybe we can do a simple spans and then just have a link slab to not have a joint detail. But then the University of Maine really wanted to, with Professor Bill Davids, wanted to push it to another level, which is making it continuous for live load. And so this is where the idea was first, it was a theory, but then we tested it with a specimen in the lab. And the idea is that you can have your stresses transferred from one span in the FRP girder into a concrete plug, a reinforced concrete beam plug, and then from that plug back into the next span FRP girder. And so this provides that moment connection. You will have a typical design of that reinforced concrete beam on the inside. Obviously, it's all in the FRP girder, and we are using corrosion resistant rebar there. So all in all, we are sticking with our main goal of having a very minimal maintenance bridge with really good connection. Now, it was designed in terms of conservatism. It is designed for carrying all the loads at simple spans, but we are gonna also test and see how much of the strain is transferred due to this continuity detail. So this is an actual picture of the girder and the at the pier, or well, yeah. So this is at the pier or abutment, similar to the sinusoidal ridges that you saw on the top flange. They are on the webs and the bottom flange, and it is designed with the same intent as the Chapter 5 inertial shear friction connection between concrete and concrete, except that this is between the concrete and FRP. And in that, in those provisions, there's also, you always need a shear, or you always need reinforcement to be crossing the plane of the plane of shear, which is what we have doing here with all those threaded rods. So in terms of the fabrication, let's talk quickly about it. This is where we are taking it out of the mold. The mold has the camber of the girder in it. So we have calculated the deflections under the cast-in-place concrete deck, and we have added the deflections for all the superimposed, like the sidewalk and the wearing surface. And from that, we have set a camber profile for the girder. This is the girder sitting outside with a nice backdrop of snow and fog over the river. And then we have also in the right corner, we have water jetting the FRP girder after it comes out of the mold, to make all the edges look, straight and nice and pretty.
And then I'll pick back up on the durability and resilience. This is one of the items that Habib touched on. That's one of the advantages for using FRP composites in civil infrastructure applications. One of the ways that we back that up is with testing, and so we've actually put the materials that we use in both the arch bridges that we have constructed, as well as these girder bridges, through a pretty intense test matrix. So you can see examples here of what different environmental exposures and durations we've tested these materials to. It comes from the International Code and Council Acceptance Criteria 125, which was originally developed for externally bonded column wraps for seismic retrofits. But the application here is really no different. It's FRP being exposed to the elements. And the way that acceptance criteria was adopted was that the samples are exposed to these different environmental exposures for different durations, and then they must maintain at least 90% of their tensile strength and stiffness after the 1,000 hours of exposure, or 85% after 3,000 hours. And this matrix that you're looking at here shows the durations and the acceptance threshold, and then for the materials that we utilize, both the tensile strength and tensile modulus, exceeding all those thresholds. Some of these were actually tested beyond the thresholds that were listed, just to see what the correlation might be. And one of the conclusions that we can draw from this is that the environmental strength knockdown factors that we utilize in design, which are pulled from the AASHTO LRFD guide specification for the design of concrete filled FRP tubes, that those same strength knockdown factors are conservative to achieve a 100-year design life. So one of the major advantages being that these materials aren't going to see degradation like traditional materials, because there's really nothing in them that will corrode or degrade over time at these exposures. The last couple of things that we'll touch on, as I alluded to earlier, is that we are in process of drafting an AASHTO guide specification for the design of hybrid composite tub girder highway bridge systems. There's a draft being circulated right now within the AASHTO Committee on Bridges and Structures that will be in development through the remainder of 2025, with the hope to put that out to ballot in 2026. And the intent of this is very, very similar to all other AASHTO design guides. It's to provide designers with guidance on flexural design, shear connection, deflections, gives a basis for material properties, the resistance factors that we talked about earlier, distribution factors, like either closed formed equations or allowing for other methods like FEA, and the idea being that engineers could design from the start. They could provide QA validation on calculations, or they could perform a load rating for this structure type in the future. So that's a resource that we are continuing to develop, and something for the design community to be aware of, that we're pushing that forward with the hopes that we'll have that validated for approval and publication in 2026. And lastly, before we enter into questions and answer session, I just wanted to kind of leave you with the thought of why composites, why to think about composites. Usually we lead with this, but this is something that we wanted to wrap up with, that obviously we have degrading infrastructure throughout our nation. We've seen structures both become functionally obsolete or are structurally deficient. And one of the tools to put in the toolbox to address that concern is to utilize composites where it makes sense. So obviously we've touched on the durability and resilience of the materials themselves being corrosion resistant or corrosion free. The actual manufacturing processes, as you saw from the fabrication photos that Anthony posted, having lighter weight materials, low energy to produce, certainly helps with the sustainability of the overall embodied energy. We also think that from an asset management standpoint, having materials that are not going to corrode is going to provide for lower life cycle costs over the life of the structure and less maintenance. And we, as we touched on from the design perspective, where we optimize our mechanical properties by changing the layers along the length, we're reducing and eliminating the waste that's in kind of excess material being in the girder where it's not needed. And as Habib touched on, we've done a lot of testing, both static and fatigue, to show that these materials do exhibit excellent fatigue resistance for the increasing demand that we place on our infrastructure. And the high strength to weight ratio also makes them great candidates for superstructure only replacements, where you might want to span over the existing abutments or utilize the existing abutments by utilizing a material where the superstructure is lighter weight. So all of those are different considerations. Obviously, where you have heavy corrosion in saltwater applications or using road salts, those are certainly applications where you should think composites. With that, we'd like to open up into a question and answer session and take questions.
All right, thank you for a great presentation, very informative. And so at this point, we are going to turn it to Paul Lyles and Don Rick Liptic to moderate the question and answer period. Paul?
Okay, Atorid, thank you. And real interesting. We have a few questions that came in during the presentation. I think we'll get some more in a minute. We have some questions that came in pre-webinar. We'll go to one of those first. What is the long-term deflection due to creep for this structure type?
Well,
this is something that we definitely were thinking about before, and we actually had done one specimen where we have left it under the weight of its concrete deck to monitor the creep deflection. We have seen some creep deformations, and so that is accounted for in our deflections table for calculating the camber. It is for this project is roughly around the 30% or so additional over the dead load deflection. But it comes with a lot of factors that can either help with that creep, and that all depends on the laminate schedule of how much carbon you're using versus glass, and also definitely the construction sequence, whether it's a cast in place or precast concrete deck.
Okay. This next question, and you might get slide 18 in the second presentation up. I think y'all kind of covered it. It says, how does the FRP stand up to UV rays or sunlight?
Yeah, that's an excellent question. One of the test protocols that was utilized in the durability test matrix, the acceptance criteria 125, is UV. It's a direct exposure to UVA light, and it cycles between dry heat and condensate. And we actually saw excellent performance when we had that direct UV exposure on these materials. And these were materials that were not coated in any way. They were raw materials. We didn't provide any sort of a UV blocking layer, a UV inhibitor, or paint. So it was just the raw materials themselves and direct UVA exposure.
Okay, you mentioned UV there. I guess the middle of the thing. It says 800 hours cycle between 60 degrees dry and wet.
Yep.
Is that a intense ultraviolet? How do they relate that to sunlight?
Yeah, it is. It is a direct UVA. The samples are inside of a UVA chamber with direct UVA exposure, and they're held off of the light only a few inches. And it is difficult in some regards to correlate testing within a lab environment to field performance. But certainly with ultraviolet, especially in a bridge structure, you're going to see more exposure on the upstream or downstream girders and the fascia, and you might get some reflection off of water surfaces, but the exposure in the real world is going to be lower than what's applied in the lab with this direct UVA exposure.
Okay. Another question, would it be possible to repair FRP beams in the event of an overheight truck accident? All these were over creeks, but I just was wondering, someone was wondering about trucks.
Yeah, oh yeah, we get that question all the time. So we actually had opportunity in the lab. Well, actually, we built a girder, and we actually did a repair on that girder, and it was a pretty extensive repair. And we took it to the lab, and we tested it to failure, and it actually performed better than the pristine after we did the repair. So we had a couple DOT folks there, and they just threw up their hands and they said, well, that answers that question. So these can be repaired. They're easily repaired. They're not, it's not complicated.
Okay. Another question that came in beforehand, was there any type of advanced wireless sensors that you plan to install on the bridges? Remote sensing?
Yeah, for the Stillwater project, there will be girder sensoring installed as part of the University of Maine's efforts on this project. I think the specifics of that particular system is still in development, where those are going to be located. But I know that there is going to be sensors installed on a few of the girders. There will be a local data acquisition system and camera system to correlate the observed strains and stresses to the traffic that's on the bridge. But the specifics of those systems, we don't have detailed quite yet.
I may add to that here, Paul, that the bridges we built already, like the grist mill bridge, for example, was also heavily sensored. There's fiber optic sensor lines running down the entire length of the girders. It gives us strains and throughout the girder, for example. So not only the new bridges, but the existing bridges were heavily instrumented as well. So.
Okay. I guess we can go back to slide 18. The next question came in during the presentation. Is the finished and cured polymer itself considered flammable, and what is its resistance to an external fire threat?
Yeah. So the matrix material that we use, the resin system that we use, does have fire retardant additives to it. And that the arch projects that we've done, actually, we took an arch bridge and we subjected it to both small scale coupon testing as well as a kind of a full scale test. It was done up to 1 hour of exposure. We did see at elevated temperatures that you do get the resin starting to burn off, but the performance of the structure was actually pretty substantial. We actually brought those arches back to the lab and tested the residual capacity after that flame exposure, and we did have almost 50% of the original capacity still in place after that exposure. So yes, there is a UV additive, but much like any other structure, if the fire is severe enough, there is going to be damage and deformation that is catastrophic. So we've got to, just like everybody else, you got to factor in the duration of that exposure and the level of heat that it produces. And small scale fires, not going to be an issue. If it's a oil tanker under there for several hours, it's going to be similar to any other structure, have some permanent deformations and need to be either repaired or replaced.
Yeah, go on.
I may add to that, the test that Tim's talking about was, there was 2 side-by-side tests. One was the composite arch, and next to it was the steel girder bridge, and they were tested under the same fire conditions in essence. And it did, of course, it outlasted the steel. The steel itself started bending and deformed as you would expect it, and whereas the arch stayed intact longer than the steel girder. So.
Okay. The question came in during the presentation. Have any of these bridges been built on the interstate, and are any being planned for the interstate in the future?
None of the bridges built to date have been built on the interstate system. The one in Stillwater, that is part of a state route, but not on the interstate itself. There's no reason why it couldn't be. Obviously, we're designing to the AASHTO LRFD standards, so there's no prevention from designing for that application on our end. Just a matter of finding the right applications, and we would certainly do them on the interstate system.
Okay. Have any of these bridges been built with full depth deck panels, and are any being planned for that in the future?
We haven't built any with full depth deck panels in the sense of like precast panels added to the girders themselves. The Cottrell Bridge in Rhode Island did utilize a full depth PBU, so the actual full depth of the deck was precast onto 2 girders with a closure pour in the field, a 2-foot wide closure pour. So that was more of a prefabricated bridge unit than utilizing precast deck panels on top of the girders.
Yeah. The first test specimen that we did at the lab, a 40-foot test specimen, did have precast deck panels that were, the undergrad students at the time did build the girder specimen as a contractor would do on site, and it had channels for the shear connectors, and those were all filled. And obviously the girder was instrumented, and we picked up the strains as that work was being done.
Are you using advanced concrete mix designs as well, or is it a normal concrete?
No, yeah, just a normal deck concrete. We use the standard specifications for whatever DOT, their standard class mix for their decks in the girder projects. For the arch project where we infill the composite tubes, we do have a specialized SCC mixture. But for the girder technology, it's just a plain reinforced concrete normally it's a 4,000 psi for most jurisdictions. Some do with 5,000.
There's no reason not to though, but it is more expensive and not needed always.
Okay, there's a question here. It says, did you add anything like macro fibers into the supports of the girders?
No,
Just regular concrete.
Yep, for the concrete, it's just a reinforced concrete section. Typically, we have seen if an owner is selecting composite tub girders, they're utilizing non-corrosive reinforcing as much as possible in their deck systems to try and match the longevity. So we'll see a lot of bridges that use GFRP reinforcing for their decks, or stainless steel or chromium where they have bent bars to supplement.
Okay. The idea that the deck replacement will be easier than traditional materials was mentioned. You said you didn't have to jackhammer it. Then has a deck replacement happened, or is this just theoretical? And could you explain how the deck replacement would happen?
Yeah, we actually hope they don't have to. It'll last as long as the composite, and because it's got non-corrosive reinforcing in it, what can go wrong, right?
Yeah. So we have tested we built a full-length bridge section in our laboratory and did the deck placement, and then we also removed the deck as well, so to demonstrate that it could be done. So that was done in the lab environment. We haven't done it in real world as well because we haven't had a deck for 40 years out there yet. But we did all that in our laboratory and proved that it could be done.
Okay. What is the cost per square foot of the bridge of a bridge deck for this? That's the cost per square foot of bridge deck for this type of bridge. Did y'all figure one of them out?
Yeah, it varies obviously depending on the bridge and the particular layout and geometry. I will say that it's typically in the order of 10 to 15, 20% higher than a traditional concrete or steel solution. A lot of that, I believe, has to do with the strength knockdown and environmental knockdown factors and statistical reliability factors that we're utilizing. So as a newer material into the civil infrastructure application, where we don't have as many case studies, as much research backing up both the load distribution side of the equation as well as the resistance side of the equation, we do take a higher knockdown on those strengths and stiffnesses, which translates to a higher upfront cost. But we also have seen that can be offset with factoring in life cycle. That was actually the Sun Island Bridge that was shown in South Pasadena. That was a competitive bid against plain reinforced concrete slab beams, as well as a stainless steel reinforced concrete slab beams. And the owner chose to go with our system because of the life cycle cost savings over the lifespan of that structure.
And I think also that depends on it's very site specific what the costs are. And there's some sites where if you've got a pretty significant skew to the bridge, it's a place where, if you're along the coast and you don't want to use steel, it makes sense to use a composite solution, especially with high skews.
Okay. A similar question, how does the girder behave if there's a fire on the surface pavement of the deck up above?
I think it would perform better than if it was a fire underneath where it's got all the insulation of the concrete. The testing that we did was direct flame exposure to the composite material. So I would say any fire that's on the top surface is going to have better insulation through the depth of pavement and the concrete deck. So I think that would be a scenario that's better than having a fire underneath.
I think the other thing I wanted to mention was that all the tests, this is self-extinguishing. In other words, if you have a fire, the girder itself doesn't catch fire. It softens, I guess to say, but it still has a lot of residual strength.
And I would like to highlight whether the construction sequence is a precast deck or a cast-in-place deck. If the deck is damaged by a fire or other factors, the girder still has a significant moment capacity and shear capacity. Maybe not up to the HL93 load, but definitely a lot of other service loads would be fine on the FRP girder.
Okay. Got some technical questions here about, let's see. The span to depth ratio is between 15 to 19. Can you use shallower depths?
Yeah, we certainly can. That's another kind of optimization, I guess, that wasn't really covered today, that we can do shallower depths for different spans. We looked at a structure in Florida, actually, that was about a 100-foot span utilizing a 24-inch deep girder. So it certainly depends on the application and what the project parameters dictate. We have some bridges where you need to have a certain hydraulic opening or a certain clearance box. So we can certainly design around those parameters. It's not necessarily restricted to certain depths. This particular project that we covered today at Stillwater, we have plenty of clearance beneath the structure for the 100-year flood. So structure depth wasn't an issue, but we have had other projects where we have to design around the depth requirements.
I think the thing to remember, I think it's kind of a point too about that, is that we can control the mechanical properties of the girder by adding carbon, adding thicker components. It's a little bit different than steel and we can vary the mechanical requirements as you go along the girder, as you can see by our method of having it in zones. So we can design those zones and we can add the material to those zones that we need. It's a very efficient type of way to design. So if you come to me and say, hey, I got this bridge, it's going to be 80-foot span, and by the way, I only have 28 inches of clearance, or whatever it is I need, I can only have a 28-inch girder, that's designable. That can be done, and there's efficiencies there that make it a good cost as well.
Okay. These bridges were constructed in 2020 through 2022. Do you have inspection data or have you seen any service issues so far?
No.
Yeah, we haven't seen any service issues. I know Maine DOT being on a biannual inspection schedule, they will have done inspections on these bridges. So certainly encourage anybody to reach out to the Maine Department of Transportation or Rhode Island for that matter. The project in Florida was for a private owner. It was not part of a Florida DOT. So I would recommend reaching out directly to either Rhode Island DOT or Maine DOT for their inspection. I know there has been a lot of development recently on from FHWA on inspection of composite materials in the bridge infrastructure market. So there's definitely ongoing guidance coming, but to see what's been done to the projects that are in service to date, I would certainly recommend reaching out to both Rhode Island DOT and Maine DOT.
Okay. Have you received new projects beyond 2022? Maybe the one we're looking at.
Yeah. So the one that we're looking at is currently the project taking up most of our time, but we did have some arch projects within that, but there were no girder projects in 2023 or 2024.
Okay. Have you conducted MASH tests on the barrier, or is it just basically a concrete barrier with a deck, like a normal bridge?
Yeah, it's normal. Whatever the jurisdiction utilizes. There's nothing special about the barrier system with the girders. The one that's being utilized on Stillwater is a modified Hawaii concrete rail. That was selected by Maine DOT. It wasn't something that we had input on, but certainly can utilize any barrier system that would traditionally be used by the owner.
Okay. Placing concrete at the end could produce stress concentrations. Have you conducted fatigue tests to see if this could be a problem?
Yeah, so with the specimen that we did, we have had this exact same detail, just a bit scaled down. It was girder cross section that was about 2 feet depth, and it matched the stresses that we are calculating for this project. And in there, there was concrete at the abutment side of it, and then concrete to make that continuity detail. It did not show any signs of strains or excessive stresses there during the test that went up to failure. So there's the paper for that specific test, I think, should be coming out soon. I think Professor Bill Davis and the grad student are in the final phases of working on that.
Question, the shape is the same for the girders, but stiffness is different. How do you justify using the AASHTO LRFD specs to calculate the distribution factors?
The girders, so all girders within the cross section are the same design. So we don't vary the girder within the cross section of the bridge. So girder 1 through 5 in that typical section are going to be the same.
Okay.
Mechanical properties.
I think it might be, the question might be the difference between a concrete beam and an FRP beam. Yeah, I agree. Our bottom flange is stiffer, but I was talking more about the overall EI, the overall rigidity of the beam is closer to an RC beam.
Yeah. The other thing is part of the research done by the University of Maine, ASCC, is the first bridge, the grist mill bridge that we showed initially. Those distribution factors were verified that we were using as conservative, because we did the load testing, all the strain gauges, everything. They developed the distributions from that, and that'll show up in the guide spec.
Okay. Compared to test data, how does the suggested design approach compare?
I mean, excellent. We've seen all of the in-service testing that's been conducted is validated or exceeded the expectations out of the lab. I know that both the grist mill, we've kind of harped on that one being load tested, but Rhode Island DOT also load tested the Cottrell Bridge in Westerly, Rhode Island. And so all of the field data that we're receiving is that, we're seeing good correlation with the design assumptions.
Yeah. In fact, I think it was Rhode Island had part of the specifications for the project we did was we couldn't deflect more than, what was it, 3/4 of an inch under full load.
I think it was less than that.
Less than that.
0.2 inches.
They actually put a deflection maximum on it and said, when you do the load test, we don't want to see any deflection higher than this. And it was pretty minuscule.
Yeah, and we are designing them with L/1000 for when there is a pedestrian sidewalk, and then L/800 if just live load.
I'll get one more, and I'm going to go ahead and turn it over to Rick. What are the main barriers, technical, regulatory, or financial, to more widespread adoption of FRP composites in state and national transportation infrastructure?
Well, I think one of the things would be the guide spec, getting that balloted and in place. A lot of people ask that, and then the other thing is like any material that you use, you're always managing the supply chain in terms of making sure that you can have really cost-efficient supply chains. And I think once you get the quantity, the volume, that will definitely bring the cost down.
Yeah. There has been composites used in the infrastructure industry for years now, and then early 2000s there was an FHWA, grants and a few with a lot of composite infrastructure that went out. I think what we are trying to do here is using more of the off-the-shelf products to, drive our costs down and, stay more competitive with the market. So that's another aspect of it.
Yeah.
Okay. It's about 10 after. We have a few more minutes. I'm going to ask Rick to come on, and there are a few more questions here, and I'm going to let Rick get them. Rick?
Yep. Hi, Paul, and thanks. You guys, great presentation. Question I seen here at the bottom is between you have diaphragms or cross frames between the box units, that were separate support for like when you poured the concrete and stuff?
No, not diaphragms from a structural standpoint. In some cases, we've had utility, hangers that are attached to from girder to girder. But being a closed box shape section, we have excellent torsional rigidity, so we don't need diaphragms for lateral torsion resistance.
Okay. There was several questions interested in, say, the compression zone over the piers where you had the live load, continuous for live load, and how do you, adjust the length of that concrete? I think you had a thickened or a concrete area over the pier, and how do you, come to grips with the transfer of that compression force and that bottom flanger and that bottom area between the concrete and the FRP as it goes through that?
Yeah, so in a calculation kind of thing, over pen and paper, your moment at the pier, your theoretical moment, and then we know from testing what the shear friction connection can handle for stresses. So that's, the quick and dirty way of calculating it. However, for this project, one of the research engineers at the University of Maine, Andrew Skank, also did FEA analysis on how long that concrete plug would be also. So, there are multiple approaches to it. And then in terms of having those compressive stresses on the bottom flange, we know how to design the composite laminate for the compressive strains versus the tensile strains and just making it more efficient.
Okay. Is there a way to inspect the inside of those girders?
Yeah, so between the end bulkheads where the concrete plugs are, we do have a drain hole that's utilized, which could be used for inspection. It would have to be through like a video scope. It's not a very large drain hole, but certainly could be done for visual inspection using a camera scope.
To go up inside there, just like with the steel, some of the steel tub structures. So,
yep.
Okay. Well, with that, we're getting close to the end here. So, yeah, and I think the one that Paul, I thought was interesting, Paul had mentioned earlier was, what's holding things back here, right? That's the way to kind of close this out a little bit. Is it's probably information for people understanding the applications and the things that not to be afraid of, right? That because it's has good and bad. I like the lightweight stuff. I had a couple questions here, or a couple comments about floating these structures down a river compared to steel and stuff like that. And it's obviously there's a lot of benefits when it's light and having smaller equipment to move the things around and things. So with that, I'll turn it back to Hatorid, and he'll close it out. So thank you, guys.
All right. Okay. Thank you, Rick. Thank you, Paul, and thank you, Habib, and all our speakers. Very informative presentation, and certainly a very durable product for the bridges that we have. So on that note, we are going to conclude our monthly webinar for the May, and we hope to have everyone back with us for our June monthly webinar and our other technology transfer activity. So long.